Chaps, are you okay with the recording? Is that okay?
Yeah, that's fine. Yeah.
Yeah, brilliant. Okay, for the benefit of the video, really, I've met Gareth and Sean before, and they met me. James Tyler, who I know, but so what I want to try and do to get the group going. This group is the nucleus. You're all doing level 2, City Hall 618701, which is the air conditioning level 2 NVQ. And I know last time I discussed a bit about how things are going to happen, stuff like that. We can revise that. And also, I want to introduce you to each other and then look at the IOR, the Institute of Refrigeration, and what the advantage of that is. Not promote, well, I'm promoting it because I'm a fellow of it and I'm on the board of trustees. But what I want to do about today's session is look at pressure enthalpy diagrams, okay? Introduce you to those at this early stage. And for some reason, my battery's showing I'm going to die. Okay, let me plug that in there. Right, that's fine. Okay. And so really it's about engagement. Yeah. As I said before, I only have 3 words in my lessons. That's relax, participate, enjoy. And then the 4th one comes automatically to pass. Okay, so relax, participate, and enjoy it. Okay, you do all those 3 things and you'll enjoy every session with it. All right.
Yep.
So just a brief background to each of you, introduction, because no one knows James. I know Sean and Gareth work very close together. So just a few words about what work you're doing, who you're working for, and any interest and hobbies, stuff like that. That's okay. We'll start with James.
Yeah, no worries. I work for ADI.
Mm-hmm.
One team, but we are doing the refrigeration and air conditioning side.
Mm-hmm.
Working on most stuff, chillers, refrigeration, AC, splits.
Brilliant.
Yeah.
I must admit, I'm really dark in it. Actually, probably better that I am in the dark because it takes a lot on keeps me out of the limelight. No? Okay, thank you. Sean, for a brief.
Work for MTech Climate Solutions.
Mm-hmm.
We pretty much do everything. Like today, I did a compressor change on a chiller. Tomorrow, I'll be working on a ducted system that's causing leaks and stuff. So we kind of do it all, but our main line share is that we are an air conditioning sort of chiller company. Hobbies, I try and play golf, which I'm no good at. That's about it.
Yeah, what's your handicap, Sean?
Oh no, I'm not even at that level yet. I've only been playing like a year and a half, maybe.
Okay.
Keeping it straight is the main thing right now.
Yep. I think for me, it's just connecting the ball with the club head. I think that's the problem.
That's exactly where I'm at.
Okay, Gareth, please, just a quick.
Yeah, same as Sean. Work for MTech Climate Solutions. Mainly come from an install background.
Okay.
And yeah, we do a bit of everything, sort of thing. Hobbies, too old these days. Used to love playing football, but too old now. So.
You're never too old, I must admit. Okay. I mean, you all know me. I'm not going to go into that scenario. But what I want to look at today is look at pressure enthalpy diagrams. And every engineer, whether you're doing the F-gas, you're doing the NVQ level 2, you're doing the NVQ level 3, or you're doing the endpoint assessment level 3 now, standard, you need to know about pressure enthalpy diagrams. And they're a great way of understanding the basic refrigeration cycle. And what I want to do really, I want to actually have a look at, I've got some handouts and publications which are on the IOR website, which is the Institute of Refrigeration website. And as your apprentices or trainees, I can get you free membership for a year, which means you have free access to the publications and masterclass and stuff like that, which is really, really good. It's a good resource. And I'll be, a lot of my training is based on that. Okay. And so I want to share that with you. And also I want to have a look at, say, the handouts publications, because I've been asked to actually revise those handouts to bring them up to speed to level 3, and that's what I want to go event later. So by way of kick-starting it, I want to see if I can share screen, okay? And I want to share screen. Okay. Right.
Because I've just been looking through that email you've sent Paul.
Yes.
And I'm up to like slide 6. I am understanding bits of it, but I'd love to go through
Good.
a lot
All
of
right.
it with you.
That's fine. Not to worry at all. We can pick up on that as well. I wanted to look at. We've got that one. That one there. I think what I might do. That's not in there. There should be another one. Let me just find another one. Okay, right. Shouldn't be here. Right. Okay.
One sec.
Right. Can you see the screen now or not?
I can still see a picture of you.
Can you see the handout or not?
No.
Any publication?
No.
Okay. Let me just go back into here and have a look at. Right. What about now?
Yeah, I can see that now.
Yeah, I can see that now.
You can see the screen. Okay, brilliant. So what this is on the IOR website, Institute of Refrigeration website, and basically it's a website for members and for students as well. Okay, you register by giving your email address. They'll send you a passcode, and then you can actually link into that. And without getting into the actual website, maybe I should actually get into the website. Right, so if I look at this now, here, right, right. Can you still see my screen?
Yeah,
Yes.
yeah.
Okay, so if I go, what I'm saying is, if I go back, if I can go back, right. So this is the IOR website, and it's ior.org.uk. Okay, and then you register. So, for example, I've signed in already, but I'll sign in again. Okay, sign in. That's me logged in there, and then there's a whole host of stuff that you can get. Okay, and as you're my trainees, it's open to everybody. I'm not saying I'm special, but because you're enrolled on a program, I can get you 12 months free subscription as a student member of the IOR. Okay, and that means you have access to this website free of charge. Later on, I think they might charge like £43 per annum. It's still worth it. So if I look at here, if I go to technical, for example, and I look at publications, okay, publications, then I can go into here and I can technical publication. There's publications and webinars, technical updates, technical RSA.
My screen's just still saying pressure enthalpy. There's nothing changed.
Is it?
Yeah.
Oh, it's paused. Sorry. Okay.
Same.
Right. Let me have a look at that now. I might need to start and then go back again. Right. Okay. Right. Let me just try that now. Okay. Can you see this now? Is that better?
Yes, that's it. Yeah, that's right.
I do apologise. I'm not an IT geek, so to speak. Okay, so welcome to the Institute of Refrigeration for experts in refrigeration. And there's a whole host of things. They have seminars, they have meetings, they have webinars, a whole host of stuff. Okay, and I'm just going to pick up on education. Okay, in the sense that under education you've got links, education careers, public apprenticeships. That lot there, the whole load of membership, environment, education, education, careers, qualifications, apprenticeship, IOR e-learning programs, creating information resources, how does the fridge work, finding local bits and pieces, and then there's fantastic and master classes. Okay, that's something I want to be looking at in a while. And also, if you look at the technical publications, for example, then I can search anything. For example, if I looked at refrigerants, I can put refrigerants in, and it'll give me all things on refrigerants, copper pipe, challenges, the whole host of things. So it's a really, really good resource, and it's ior.org.uk. Okay, there's that. So that's really, really good. And what I want to focus on is really looking at the publications, which I think I've got here. Let's have a look at this one. So I'm going to start with this one here. Okay, can you see that, guys?
Yeah.
Yep, brilliant. So what we're saying here is we've got a pressure entropy diagram. Okay, we've got a pressure entropy diagram, and basically this is on the web. Okay, I'm just going to make it bigger. Okay, so what we're saying is here we've got the compressor, okay? We've got the condenser, we've got the expansion device, we've got the evaporator, and then we've got the suction line going back to the compressor, discharge line from the compressor to the condenser, and then from the liquid line to the TEV expansion device, expansion line, and back into the evaporator. Okay, so what we're saying here is that the second in the RSCHP engineering technician section fundamental series covers pressure temperature relationships using pressure entropy diagrams. This follows on from the basic cycle diagram explored in F1. This diagram illustrates the fundamental processes of evaporation and condensation. The diagram represents the process in the refrigeration system in a way that makes analysis and evaluation of the process become easier. Okay? A pressure entropy diagram, which determines system operating conditions, temperature and pressure, can also be used to estimate system operating capacity. Pressure entropy diagrams are still used as the main tool for analysis of refrigeration processes. There are software packages that can perform the same analysis faster and with more detail. The chart shows the temperature enthalpy characteristics of a refrigerant at different pressures. The left side of the curve is saturated liquid, and the right is saturated vapor. The top of the curve is critical point, and the area in the middle, liquid vapor mixture. So I'm not going to go into, I will actually go into bits and pieces. So we've got the system here. Okay. Now this is the representation on the pressure entropy diagram here. Okay. In the sense that we got the compressor, we've got the condenser, we've got the expansion device there, and the evaporator. And chaps, let me show you, tonight's session will actually enlighten you and give you a lot more information. This is just by way of introduction, to promote the IOR and also to give you an indication of what's what. Okay, so we've got that bit there on pressure entropy diagrams. Now this is exactly what a pressure entropy diagram looks like. Okay, and you get one for each different refrigerant. So you could be on R32, you could be on 404A, 407F, 410A. Okay, there are diagrams for R22 which are phased out, but any refrigerant, ammonia, they've all got their dedicated pressure entropy diagram. Okay, we've got some definitions here. Now, this is the handout I've been asked by the IOR to revise later, but I thought I'll share it with you, and then you can, you'll see the before, and then not now, but later in the future, the updated version. So glossary thing got saturated liquid. I think I was asking Sean and Gareth some of this terminology last time, and I want to pick up in the sense that saturated liquid, it's a liquid which is at the saturation temperature, boiling temperature. So for example, water boils at 100 degrees C. So saturated liquid would be water when it just starts to boil. Okay, 100 degrees C. At this point, any additional heat applied to the liquid will cause part of it to evaporate. Saturated vapor is a vapor which is at the saturation temperature. So think about the water. It starts to boil off 100 degrees C. James, no, there's no need to take any notes. Okay, there's no need to take any notes because this is being recorded. If you can take some notes, by all means, help yourself. What I'm saying is, if you focus on what I'm showing you, what I'm discussing, then that will follow. Okay. I know as engineers or students, I've got to write this down. The beauty of doing it this way is you can concentrate on hearing, listening, and observing without having to write. Okay?
Oh, okay.
When there is a time to write, I will ask you, and I'll actually set you some questions. But
no
certainly, I just wanted to take notes. If there are any questions, guys, please ask. All right.
Yep.
Yeah. So what I'm saying, saturated liquid is liquid as it begins to boil at the saturation temperature, which is boiling temperature. Saturated vapor is when it has boiled, so it's 100% vapor, but it's still at the boiling temperature. So, for example, you've got water at 100 degrees C. It starts to boil. We add heat, and it becomes part vapor, part liquid, until eventually all the liquid boils off, then we get saturated vapor. Okay, that's the. Now, subcooled is when the liquid has been cooled below its saturation temperature. So, for example, if we look at water again, now water boils over 100 degrees C, and if we had water at, say, 75 degrees C, it would be subcooled because it's below its boiling temperature. Yeah. So water at 75 degrees C or water coming out the tap at 12 degrees C is actually subcooled liquid as a substance. Okay, so subcooled is where the liquid has been cooled below its saturation temperature, below its condensing temperature, below its evaporating temperature. Now, superheat, the opposite, is where the refrigerant is above its saturation temperature. So, for example, if we take water, we say, right, it boils over 100 degrees C. If we add more heat into it and raise its temperature above boiling, say, to 120 degrees C, then that's, it's superheated vapor. And for the gas engineer, we call it superheated steam. So superheat is above boiling, saturation is at its saturation point, and then subcooled liquid is below the condensing point, below the boiling point. Okay, does that make sense in initial terms?
Yes.
Yeah.
Yeah.
Brilliant stuff. And what we're saying is, just by way of the pressure enthalpy diagram here, we've got pressure, okay, and that's absolute pressure. So that'll be gauge pressure plus 1 bar atmospheric. For example, if you've got gauge pressure and that's showing 2 bar, then your suction pressure will be 3 bar absolute. If your discharge pressure is showing 15 bar gauge, it will be 16 bar absolute on the pressure enthalpy diagram. Because we're dealing.
Can I ask you a question, Paul?
Of course you can.
You're saying that there's a different chart for each gas.
There is.
So where you go, so looking at what you're looking at now from A to B.
Yes.
That on a different gas, that might be taller or shorter because of the different pressure it's needed to be.
And it could be anywhere along here. It'll shift. We always get the shopping trolley shape, as I call it. Okay.
But
and it always goes anti-clockwise. Always on a pressure enthalpy diagram, it's always flowing from that to the evaporator, the bottom horizontal line. Right. The diagonal line is always the compressor. Then the condenser is always the top horizontal line, and the expansion device is always on the left-hand side. It's always vertical. Okay, we always get that basic shape, but you're right in the sense that there could be shallow, it could be narrow and tall. Yeah. There could be long and fat. Yeah. So depending on the circumstances of how the system's operating. So I want to leave that for now. Okay. Just want to stop share. Right. Any questions?
1 second. I noticed I need to charge my laptop. 1 second. Just go grab my charger.
Yeah, just plug him in. No worries. We're just waiting for Sean, if that's okay.
Yeah, no problems.
Right. Okay. Right. So, whilst we're getting that for Sean, I'm just going to share screen and move towards the masterclass. Okay. In fact, chaps, I just realised I did send you a late email with the PowerPoint presentations on. I don't know if you just this evening about 6:30.
Yeah.
don't know if you picked that up.
Yeah, I've got it. Yeah.
James, did you pick it up?
I haven't seen any. I'll have a look.
James, I
Hold
can't
on.
hear you.
I said I'll have a look.
Yeah, well, not an issue. No, what I'm saying is the masterclass I did for the IOR is a webinar on the 7th of March, I think it was.
Yeah.
And those PowerPoint presentations is what I use for the actual masterclass. So what I'm saying is the handouts, the slides that I'll be discussing, talking about, you have as well. Okay.
Yes.
To give you more information. What I want to try and do is, if I can, I want to now go to that's the presentation slides, and I want to go to masterclass. Right. So if I go to here, and then if I go to here. I'm just going to close this guy. I can close this one down now. Okay. That'll come later. I can close that one down as well. Right. These are the presentation slides I sent across to you.
Yeah, that's what we got in the email, isn't it?
Yeah, only recently. But what I'm saying is, what I've done, I want to get onto here, and I should be on master. This might be this. Yeah. Okay. Right. So, what I'm going to do is really this presentation, a webinar, I delivered on 7th of March. Okay, and it went out to the industry, and I'm just going to. All I'm going to do is I'm just going to play it, if that's okay. Yeah. And what I might do, I might take some screenshots for publicity, bits and pieces. Because I'm very much into LinkedIn and stuff like that, promoting it. So I'm just going to take a shot here now. Tuesday and Thursdays. Right. So what I'm going to do, I'm just going to, if you can just observe, listen, okay, I'll be here. And I do apologize for any mishappenings, but this is the Institute Refrigeration typical masterclass. Okay.
And we don't have to take any notes because it's still being recorded.
Don't take any notes. No. Okay. Yeah.
Hello everyone, and welcome to today's masterclass. My name is Lisa Waters, and I work for the Institute of Refrigeration. And I'm delighted that you've joined us today. We have a fantastic speaker today, Paul Singh. Paul, there you are. I'm so pleased that you've joined us today, and I'm really looking forward to this presentation today because I have never understood refrigeration, so I'm hoping that you'll be able to get it through to me. Before we kick off your presentation, I just want to have a quick conversation with you. Obviously, you've been involved in the IOR for many, many years. As I believe you're a fellow of the Institute. So can I just ask, why are you so heavily involved in the IOR? What do you gain from it?
I get a lot of information that I share with my clients, my students, and there's a lot of information out there that students can use
and I use it as a consultant as well. That's one thing, the actual applications. Also, it's the different websites we've got fantastic fridges that I've been helping develop for youngsters, engineers, and so on, apprenticeships, and level 2, level 3 programs. So that's fantastic. Also, it's the ethos of IOR, we're one community, and the whole industry getting together. I must admit, although I'm not a very good networker, if I'm honest. I do thoroughly enjoy the industry. It's a passion of mine, it's a hobby. That's played me well. And I want to share that knowledge with the IOR, my expertise, and with the ROC industry per se. Understanding pH charts, another term for it, molecular diagrams. And it's obviously today, and I'm Paul Singh, a lot of people know me, and I actually own and run Chile Training Academy. And if I press this button here, there's the context. So what we're doing is brief introduction, basic refrigeration system, basic pH chart, azeotropic refrigerant, simple R408 refrigeration system, pH chart plotting and calculations. I'll be going into a level 2 sample question, multi-choice of the City Law 609502, and also finishing off with a level 3 question that the current cohort of apprentices on EPA standard program is a sample test paper on physical virtual. By way of introduction, I've been in the RSS industry for over 45 years now. I actually started in 77. I own and run Chile Training Academy. I'm also a parent governor. Children go there, and in fact, I've got a parent governor meeting this evening, which is really good. The other one is I'm also off-ball RSC, being subject matter expert. I'm chairperson of the BSRO, the local society, the Birmingham Society of Refrigeration and Air Conditioning, and I'm a fellow of the IOR. And one of the things I had a passion about was actually joining the IOR Publications. And I'm glad to say that I got elected. I was actually listening in November to see what results. So I'm really keen with that and eager to get more and more involved. And I must admit, those people out there that consider being Board of Trustees membership, if you don't get into it first time, apply. It took me 3 attempts to actually become elected, and you get better for it. Yeah? So that's a lot about me. The other thing I want to say is that, just a reminder, this presentation expresses my views and those of all prices, and not necessarily the IOR. That's important. Okay? So what I'm saying is, it's not the opinion of the IOR, it's actually all seen gained over 45 years experience. So I want to kick off with the basic refrigeration system. Okay? So what I'm saying is, here's the basic refrigeration system here. I'm not going to go through it entirely, but here we've got the component there, some components there. Now,
I'm just going to.
So here's the evaporator, and that's where we actually.
Can you see the screen? No, I can't see anymore.
And that heats it.
No, it's just
No.
gone back to picture view.
And then that goes to the condenser, and then we've got the expansion valve. The expansion valve. So
Right, okay.
TV.
That's all we are.
So it's an expansion valve.
But what I'm going to do is I'm just going to. It's me messing about. That's it. Let's just leave it there. We've got that there. Right. There we are.
And so what I'm saying is, here's the basic refrigeration system here. I'm not going to go through it entirely, but here we've got the component there, some components there. So here's the evaporator, and that's where we actually absorbing heat. Okay. And that heat is by the compressor, and then that goes to the condenser, and then we've got the expansion valve. Some people call it TEV, thermostatic expansion valve. So in simple terms, we've got the evaporator is where, if you think of your fridge at home, the box, that's the evaporator. You know, taking heat out from your fish fingers or bacon or carrots. And that heat is going into the compressor, and that compressor is heat so that it actually has a higher temperature, high pressure, so it can ejected a condenser, and when it leaves, it becomes a liquid again. So it goes through the expansion device, which reduces the pressure and temperature. You reuse it. So it's an ongoing cycle. Four main both. You've got evaporator, compressor, condenser, expansion valve, and the direction flow is from the evaporator to the compressor, to the condenser, from the condenser into the expansion valve thing. And then, well, we have four interconnecting pipelines. We've got discharge lines connecting the compressor to the condenser, and then from the condenser to the expansion valve, we've got the liquid line, and then from the expansion valve, we've got the expansion line there. Then from the expansion line, go through the evaporator, and then the suction line going back into the compressor. So in simple terms, compressor, condenser, expansion valve, evaporator, four main components, four interconnecting lines, discharge line, liquid line, expansion line, and the suction. And the thing I do want to say at the moment is I'm just conscious of the fact that we've actually got three engineers doing the F-gas qualification this morning. And I know they're really listening to the presentation because this is the kind of content that's actually involved in the F-gas requirement online test practice. When I was looking at programs, one thing I'm very passionate about is India, born there, and I frequently visit India. I use the analogy of a 5 Indian railway station that I use, and the analogy is really looking at the concept of heat transfer from A to B to C to D to E, and then how the change of the actual refrigerant, the coolant, actually happens. So forgive me, it's the first time I've actually animated presentation, but gives one station, 2, 3, 4, 5 stations, and that way it's heat transfer. So what's happening is that the heat is transferring, it's going from left to right. Here, this dot here it's got the least amount of heat, okay? And this is called subcool liquid. So you've got subcool liquid. Take water, for example. You've taken it out of a tap. It's 12 degrees. You put it into a kettle, and that's going to raise its heat content, and it's going to become a saturated liquid, whereby we're adding heat, we're raising the temperature. So that's liquid. That will be saturated liquid. So water begins to boil at 100 degrees C. Then here, sorry, I've got to ask the question before. So that's saturated liquid at 100 degrees C, for example, and then we're adding heat, and what's happening is it's vaporized. This one here, that saturated mixture, it's a mixture of liquid vapor. Okay, right. So here is.
Chaps, I do apologise. I hate the presentations.
Is anyone else having problems with the audio?
And what happens basically is that
I can't hear most of what's being said. It's cutting in and out. It's like I can hear it 1 minute fine, and the next minute it's like I can't hear a thing.
Yeah, are you okay with hearing it?
He's going in and out.
Is it? What I might do. It might be the next. Let me just try and see if I can. I'm just going to stop this video for that. Stop me. That might be better.
We raise its temperature above 100, 720, then it should be heated vapor. The only difference between water and refrigerant is that everything happening at a lower temperature, very much lower temperatures. For example, we could have evaporating at -30. That's your freezer temperature. That's the temperature required for your freezer to operate at -20, and so forth. So by way of the introduction to the pressure entry diagram, here we've got pressure. Okay? That's absolute pressure. I'll talk about that. Along here, we've actually got enthalpy. Now, enthalpy is a term that we use for heat content. It's measured in kilojoules per kilogram, and it's the heat content per unit mass. So, by definition, it's heat content per unit mass measured in kilojoules per kilogram. And so, on the vertical scale, we've got absolute pressure, horizontal where enthalpy. Here, this curve is unique to any refrigerant. Okay? Depending on the refrigerants, that determines the pressure temperature relationship, and also how that curve is. You could get narrow curves, tall, you get fat curves, which are shallow. But certainly that's the making of the enthalpy diagram. Here's it's basically a chart, body diagram, and I want to talk about absolute pressure. Absolute pressure really is reference against a perfect vacuum. Gauge pressure is reference against atmospheric pressure, which is 1.01325 bars. As engineers, we think about atmospheric pressure at 1 bar or 14.7 psi. For senior engineers. So absolute pressure, we measure the gauge pressure that you'd read off your gauge attached to a system. Then we just add 1 bar. So your systems are operating at gauge pressures. When we're actually plotting pressure into the diagrams, because we're looking at thermodynamic properties and calculation of temperatures and pressures, we have to convert to absolute. So that's the refrigeration cycle, and so I'm going to talk about on this pressure diagram. So we've got the line that goes diagonally upwards. I'll tell you why later as we progress through. Then we've got a line that goes back. And we have a line that drops vertically down. And then we've got the line that goes horizontally across. So that really is the basic refrigeration cycle. I'm going to explain it a bit more. And so when we're plotting it, there's things that we need from the system to ensure we can plot it. Now, different engineers will say different things, there's different views on this. Certainly, we need to register what the discharge pressure is. So your system discharge pressure, the high side pressure, might be a 17 bar gauge. And then we've got the low pressure, the suction pressure, that might be a 4 bar gauge. And what we have to do, we have to add 1 bar to each, eventually to plot, which becomes 5 and 18 bars. So basically, the diagonal is the compressor. That's where the compression happens. The refrigerant is the compressor. So we're raising the pressure of it. If we're raising the pressure, we're raising the temperature also. It depends on the laws of thermodynamics, which college lecturers and once pressure goes up, temperature goes up, but the volume comes down. So you compress it. Now, out of the compressor, we go into the top line horizontal is condensation. The refrigerant is condensing back from a superheated vapor to a subcooled liquid. So we're getting condensing in the sense that if you're think about having a shower, you've got warm water, you've got steam, you've got a cold shower window, and you're getting mist or dew. That is condensation, and that's what's happening to the refrigerant here. We're condensing the superheated vapor into a saturated mixture, saturated liquid, and then a subcooled liquid eventually. So here it's subcooled liquid. It goes into the expansion part, and that's actually expands the refrigerant. It's actually the opposite to the compressor. Compressor is compressing it, the expansion valve is expanding it. And so we've got the expansion process. Bottom one is where the heat absorbs. So you've got the evaporation process of the refrigerant made to evaporate. And all we're saying is here that basically anything in this region is subcooled liquid. So this bit here is subcooled liquid there. Anything here is saturated liquid. So this condition there, that point there, is where the refrigerant is actually going from a subcooled liquid to a saturated liquid, and then it's going to come out here as a saturated mixture. It goes through the evaporator, it's absorbing heat, and that heat, because it's changing the actual condition, the state of the refrigerant, is what we call latent heat. So it's changing from liquid level mixture to 100% vapor here, and then we're going out to the superheated vapor. So that is the basic fridge circuit, and that line there, got that there. I'm going to talk through those, and so this red line here is what we call the the discharge line, and its discharge superheat is telling us how much of the refrigerant is superheated by. So, for example, if you use water as an example, we've got water at 100 degrees C, and it goes up to 160, then there's 60 degrees of discharge superheat, and we use that with refrigerant. Obviously, the temperature will be lower. Okay, but discharge superheat is above the condensing temperature. On the side here is where we've got saturated liquid here, and then we're taking more heat out of it. So that becomes a subcooled liquid. A bit like water, where it's boiling 100 degrees C, and we take more heat out of it, we allow the water to cool down to 75. So from 100 down to 75, it's actually subcooled liquid. Think about a submarine below the condensing temperature, below where it's liquid. This line here, that's where it's going into the evaporator, and that technically is a mixture of 90% liquid, 10% vapor, depending on how efficient the system is running. And also that there is where the bubble point is, or the bubble temperature. I'll talk about those a bit later. So going through the evaporator, and we're going into the compressor. Going into the compressor there. Here it's a saturated vapor. So we've gone above the evaporating temperature. The evaporator might be at -30, and we've actually gone up to say -25. So -25 is higher than -30, so that's superheated. It's above boiling. Just want to talk briefly about refrigerant. You can't not talk about refrigerant when it's not refrigerant. And I must admit, I've been in the trade for 45 years, and refrigerants I've seen, they come and go. Where we are at the moment today, 7th of March, 2024, we've got things like single refrigerants, we've got isotropic mixtures, azeotropic. When I was a student back in Solihull College, I hadn't heard about azeotropics. They've been introduced because environment issues have actually made that happen. It's been necessitated. So I just want to briefly talk about it. A single refrigerant is really one that has one substance. And a single refrigerant, they've got refrigerant numbers. Any fluid that the manufacturer of refrigerant manufactures, for it to be approved to be a refrigerant, it has to go through ASHRAE. And in our refrigerant number, azeotropic refrigerant have constant properties in the sense that it's a mixture of 2 or 3 refrigerants, but they don't separate. There's no glide or slide, which I'll be having a look at, whereas other refrigerants do. So again, we've got, you can recognise azeotropic refrigerant by the 500 series of refrigerant, so R500 series, like a BMW, 515, stuff like that. So as an example, you've got R507. Here, we've got a capital A. And here we've got a small a there. Now, there's a difference. Okay? And the difference is that this capital A actually means that it's one of a series of 507s, but it's got different percentages. So the capital A would mean that we've got somewhere, we've got 507A, 507B, 507, etc. And what they're saying is they've actually used R507A, which has got different proportions, percentages, as opposed to R507B, for example. Whereas this small a here it means it's a single refrigerant. Zeotropics, sorry, R507A, got R125 and R143A, and that's a mixture of 2 refrigerants. 50%. So the blend is 50-50%, and it's R507A, and they won't separate. Zeotropic blend, a lot of engineers are using zeotropic blends in the sense that zeotropic refrigerant, they have fractionation. That basically means they'll separate. They'll boil off at different temperatures at the same pressure. Technically, it's called different evaporation. For layman's terms, and ladies' terms, they're separate. And if you have a zeotropic refrigerant blend that has leaked out, then what we must do is we must recover all the refrigerant and put in new refrigerant. Technical term is virgin refrigerant, because it's lost its composition. And zero blends will have temperature glide and temperature slide, which we'll go into a bit later. But certainly, all it's saying is that it starts off at one temperature and it's evaporating, and it has to, because it's 3 blends, or 2 blends, refrigerant, so each will have a different boiling point. And we want to ensure that the whole blend is actually evaporated, saturated vapor, when it comes out of the, when it goes into the, comes out of the evaporator and goes into the suction line, it should be above that. So glide and slide. Glide is actually in the evaporator. The temperature might be at -30, and start to evaporate at -30. It might go to -27 before it's actually completely evaporated. Temperature slide is actually in the condenser, and we're rejecting heat. So we might be condensing at, say, 40, and it has to get down to 37, for example, and the temperature's gone from 40 to 37, so it slid down. Temperature slide. The evaporator, it's fine.
I've lost all audio now. Same as you guys.
Yeah, I've lost audio.
I can't hear much what's being said anyway, to be honest. And I know he's recording it, but it's just going to be the same on the recording.
Sean, can you hear it? No, the recording will be fine.
Oh, will the recording be okay, Paul? Yeah.
Yeah. Sean,
Right.
it's recording what I'm hearing here. Okay.
The state of the refrigerant around the site.
No, I'm audio's jumping in and out again on me. Not.
Is it?
We've got the
Okay.
4 main components here: compressor, the condenser, the evaporator. Sorry, the expansion device and the evaporator. So those 4 components won't change. They have to be in that sequence. But we have additional components to make the system run better.
Can I just ask, Paul, you know, what's component E and M? I was looking at this slide before, so I understand what's going on with the filter.
Right, that is the liquid receiver.
That's a liquid receiver. So what's M?
That's
Is that accumulator?
Liquid receiver. That'll be the filter dryer. That's a solenoid valve. That's a slide glass. And that's the EV.
Yeah, expansion valve.
Expansion valve. Yeah, that's it.
And then what's M down here? So follow it.
Follow through. That's the suction accumulator. That's the suction accumulator
Right, okay.
there. Yeah. So you've got suction accumulator, pressure gauge, pressure switch, compressor, discharge line. Okay. That's the all separator here. That's the all separator. And that's the all return going back to the compressor. So any all stayed at the bottom. Then we got discharge line there going into the condenser through, and the cycle repeats itself. Yeah. Okay.
Yeah.
Now what I'm going to task you with, because there's I mean I am going to record all this. I do want to record all this for the benefit of the audience, because I've got a lot of people, a lot of interested parties who want to listen in, and so just bear with me. And if there's things that you don't understand, we can go over them. The only thing I will say is that you can actually access directly on the IOR website yourselves the actual masterclass, this webinar on your own.
Right.
Yeah. See what I'm saying? I'm on the IOR website listening to the masterclass, which is recorded. Yeah. So the recording is available to you free of charge. You just have to put your name in, your email address, and they'll allow you to actually view it on your own as well, if that makes sense.
Okay.
But I still want to go through, because I want to make sure that I've got the complete lesson going through.
Run better.
Yeah.
And what that means there is basically that here's the compressor. It's going through compressor there, going into the discharge line. That's an all separator, and it's going through the condenser there, into a liquid receiver, out the liquid receiver into filter dryer, solenoid valve, cycle glass, TEV, and that's going into the expansion line, the evaporator there, coming out into a suction accumulator and into a pressure switch and a pressure gauge back to the compressor. Now, you know, I drew these 5 Indian railway stations earlier. Well, technically, there are only 5 states of refrigerants that will come around the system. Around 5 states. Remember that. Now, what we're saying is, so for example, here, number 1, that is superheated vapor. Then you've got number 2 here, that's saturated vapor. Number 3 here, saturated mixture, 50% vapor, 50% liquid. And number 4, saturated liquid, 100%. And number 5, so if I was teaching, I'd be asking the students, you know, what's number 5? And the correct answer is a subcool. And then go through the subcool liquid into the expansion device, and that's going to drop pressure, drop temperature. So coming in at number 6 here, it's a saturated mixture, low pressure, low temperature. I'm working on low pressure. Forgive me if we get this wrong. We want to absorb cauliflower meat. So it goes into evaporator at saturated mixture 19 future. If anybody knows why you evaporate it, needs to be in.
I think there's 2 playing, aren't there? Let me just get to the bottom of this. Okay. Okay. Let me just. I'm going to stop share because I've got a feeling that there's 2 playing in the background. Okay. Let's just leave that there. I'm happy with that. That's where we are. And then if I'm going to Google. I might have too many. I might have too much open on my screen that it's. Yeah, let me just share screen.
So IOR.org.uk, and then
That's right.
Just put our email address in.
And then you go to masterclasses.
Yeah.
Masterclasses. Right. So, can I just try this again now?
The liquid is changed, Danny. So we've got saturated refrigeration engineer later and liquid. Please let me know. Then number 8, at the end, towards the end of the evaporator, all the liquid boiled off. So we've got 100% saturated vapor before it goes into the suction line where it should be the vapor. And that cycle, see that it's repeating itself. So what we're saying is, look at it, we've got 1, 2, 3, 4, 5 different stages of refrigeration, and that's all we get. On the high side, we get all 5. Okay? From superheated vapor, saturated mixture, 50-50, saturated liquid, 100%, and then subcool liquid. On the low side, because we got the, I would say, the inefficiency of the expansion device, we don't get subcool liquid. Okay? What we do, and we don't get saturated liquid, 100% either. What we do get is we get mixture. So here's saturated mixture, 90-10, 50-50, saturated vapor, and superheated vapor. So there's only really technically 4 different states if you're going to look at the percentages on the low side. So that's a bit of a, you know, the state of the refrigerant around the cycle. This is an example that Paul used. 17 bar is the high side pressure, and 4 bar is the low side pressure. And that's 4 bar gauge, 17 bar gauge. That's what you'd actually get on the gauge. Okay, here we got some temperatures, 55 degrees C, and this is discharge line temperature here, 39 there. These are just temperatures the refrigerant might be operating at under these under system. So if I just go back slightly, I do apologize, I'm not used to PowerPoint. So what we're saying here is we've got 17 bar, 4 bar discharge and suction. what will happen is that depending on the refrigerant, this is R4048, we get what's known as a pressure-temperature relationship. What pressure is that refrigerant going to saturate at? So on the high side, what we're saying is 17 bar is going to condense at about 39 degrees C for R4048. That's what it's condensing at. That's what it's rejecting heat. On the low side, in the evaporator, unless I'm mistaken, then our 4-bar gauge, 4048, is evaporating at about -6. And that's the temperature of not your cabinet, not your fridge or your freezer, it's actual refrigerant inside the tubes that's going round. And normally, by design, evaporating temperature is usually 10 degrees below what we're trying to achieve room temperature. So technically, this is trying to achieve 10 degrees above that, so about 4 degrees. It could be milk in your fridge, for example. So that's just sort of looking at the basic, bit more detail with temperature and stuff like that. I want to amplify that. So we've got this system here, up there. So that's just split across. We've got the temperatures and the pressures. Now, when we're going to plot it, what we've got is we've got a 4-bar and we've got 17 bar. That's our starting point, in the sense that we've got suction pressure there and discharge pressure there. However, because this is calibrated in absolute, we've got a situation where we have to add 1 bar. So the suction pressure becomes 4 plus 1, which is 5, and the discharge pressure becomes 17 plus 1, which is 18. And we actually plot the discharge pressure along here, and we plot the suction pressure down here. And that will actually give us, it should correspond to what the actual evaporation and condensation temperatures are. We've got 4 degrees here, which is suction line temperature, and so what's saying here is we've gone from -6 up to 4, and that means that's suction fluid. That's how much the refrigerant is actually heated up by before it enters the compressor. And suction fluid, normally we're trying to get about 5 degrees of superheat. We use K for Kelvin to ensure that we don't get mistaken with 5 degrees C. And 5K means, or 10K in this case, is the difference between the suction line temperature and the evaporating temperature. We've got discharge superheat here. Again, we might be at 55 here, and that might be at 39. And that will give us a certain amount of superheat there by calculation. And engineers are required to calculate these calculations by using a pressure entry diagram. See how effective the system is. On the low side, on the liquid side, we've got saturated liquid there with subcooling it. Remember, it's 39 degrees. If you look at here, that temperature there is 39 degrees. So it's condensing at 39 degrees there. And so we've got 39 degrees condensing, liquid line temperature is 32. And then eventually I'm going to go through a process where how do we actually calculate the superheat and the subcooling. So what we've got here, I've just put some questions. So these are what my engineers are doing. What would be the suction superheat? What would be the discharge superheat? What's the liquid line subcooling? What's temperature slide and temperature glide? Now, refrigeration and air conditioning requires a certain amount of mathematics. We normally require minimum level 2, either on entry or on completion, in mathematics or maths. Again, a bit of number crunching. What we're saying here in this situation, I've changed the numbers around because I'm wary of some. On the previous slide, some engineers would know the answers already. So I want to make sure I've changed this. So we're going to do some calculations. So we're saying we've got 60. We've got a situation where you've got 64 degrees there. You've got 13.5 bar pressure. You've got 1 bar suction pressure there. Now this is on a R407C. Now R407C this capital C means that we've got R407A, R407B, R407C, and in fact, if I recollect, we've got R407F as well, which we use, and there's G around. So that's just saying we got R407C. So what we're saying there is we're going around the cycle, and we're looking at suction soup heat, discharge soup heat, liquid line subcooling, temperature slide, and temperature glide by calculation. So we could, our dew point there, it starts to condense at 38. It starts to condense at 38. It has condensed by 30 at 33. So we've got liquid. Its midpoint might be 35. I had a presentation done by Neil Roberts from Climalife, a very good friend of mine, and we were talking about the midpoints of condensation and midpoint evaporation. And some engineers tend to use that midpoint approximately to plot the chart and get further information. So here we're evaporating at -29. Start to boil off at -29. That's cold, isn't it? -29 degrees C. I've heard that they've had temperatures around about -20 in Canada recently. I don't want to be there, I'd rather be in India. So it starts to boil at -29, and it has to go up to -21. So that blend, 407C, under this condition, has actually evaporated. And midpoint approximately is -25. Now, look at the calculation, saying suction soup heat. Now, I'm not going to go into asking question mode. The suction soup heat is the difference between what we're evaporating at, or how we evaporate at -21, and the subsequent temperature. So our subsequent temperature is -9 degrees C. The temperature of the refrigerator saturated vapor is -21. So sometimes that's called dew temperature as well. So now, some engineers, wrongly, they'll say -29, -9. You always take away the small number from the big number. Okay? So the mathematical, it's going to be -9 minus -21, and the answer is 12 degrees. Because if you go to -21 minus -9, then you're going to come up with a negative number, and we can't have a negative soup heat. It's always a positive soup heat, positive subcooling as well. So we're saying suction soup heat is 12K, discharge soup heat, it comes out at 26K. How do we calculate that? It's 64 degrees C minus 38, that gives us 26. Remember, we're using Kelvin, K, to say it's a temperature difference. So 64 to 38 is 26 degrees difference. And that's a discharge soup heat. Liquid line subcooling, we've got 6K. So it's really from coming out as 33 and the liquid line temperature is 27. So the difference, subcooling below saturation, below condensing of 6 degrees. So the bubble temperature here was 33 and 27 degrees the liquid line temperature. 33 minus 27 gives us 6 Kelvin. Now, with a blend, geotropic blend, we do get temperature slide and temperature glide, because the actual refrigerant is boiling off at different rates. Three different chemicals, each one has their own boiling points at these conditions. So, for example, you've got one refrigerant here, this is -29, you've got another refrigerant -25, another one -21. Okay. On the condensing side, one condensing at 38, one might be condensing at 35, and one at 33. Now, the pressure temperature blend you can actually get from a refrigerator diagram, by all means, and also a refrigerant slider, or a refrigerant comparator. And there are apps available to give you pressure temperature relation. I must admit, I'm an avid fan of the IOR, first and foremost. I'm an avid fan of Danfoss as well, because they've got some really good tools, software packages, Danfoss slider, and that gives you a lot of information on that. You can use those. There are others as well. Don't get me wrong, there are. It's just what I prefer. Okay, so temperature slide. And if we're looking at the condenser here, we're saying, look, we start to condense at 38, and we have to get down to 33 degrees C. And that there is the temperature slide because it's going downwards. So that's going to be 5K. And if you're looking at glides, look, we're at minus 29, and it's gliding up to minus 21. So that's going to be the difference. Mathematically, it's minus 21 minus minus 29, which is 8 Kelvin. So that's looking at how to obtain superheat, subcooling, sliding glide. And this information I've drawn out is from a running system. We have the pressures, the temperatures, and we go around the discharge line with a thermometer. So we're getting 64 degrees, 27 degrees on the liquid line. The suction lines are minus 9 degrees. So we're using apparatus to get the temperatures. The actual temperatures inside the evaporator and the condenser, you can either get off the downforce output of that, or you can still get that from a pressure density diagram as well. Pressure density diagrams, you can do a lot with them if you've got the I do want to get people into teaching. Get into teaching, which I'll talk about. So here, I've just picked up the reminder, superheat vapor, the condition of the refrigerant around the system. And this is a slide we left out. I will be using this afternoon for my engineers when they're doing the F-gas. Now, pressure entry diagram, I've been using what we call skeleton pH charts. It's things I've drawn up, all drawn up. This is an actual pH chart, a model diagram for R407. And what we notice is we've got absolute pressure here, down there, up there. We've got the enthalpy here, and I can't see because of my toolbar. I might move my toolbar up here. And here we got the enthalpy per kilogram. So it's ranging from 140 to 620. And that really is telling us what the pressure is. The pressure is going horizontally. The enthalpy is going vertically downwards or upwards that way. Here we got the curve, saturation curve. There. Here we got subcool liquid, saturated mixture, saturated vapor, and all this region is superheated vapor. And this is a 407C refrigerant, and we have lines of constant temperature as well on the pH chart. So the lines of temperature are doing this, they go vertically, so they go vertically down like this, then they hit the saturated liquid, then this is actually sliding down now. It's sliding down because the blend is a electronic blend. So we're saying we've got here, we're at 0, and then that 0 goes that way as well. So lines of temperature are here, there like that, and then that way. So you read your temperatures here, you can read your temperatures in the middle here as well. Okay. And also some charts have them on here as well. What's interesting to note is that here, subcool liquid, saturated mixture, and saturated vapor and superheated vapor. Just going to look at plotting a chart. I'm going to get back to the one previous. So we've got 18 bar, absolute. Here, so we're drawing a line horizontally across. Normally with a ruler, in my case. Here we've got 1 at 5 bar, absolute, and we're going line there. Then we got, we can pick up some temperatures. We said our suction line temperature 10 degrees. So that's 10 degrees is there. It's actually, let me just get into that. I do apologize. Despite all the rehearsing you do, all the rehearsing I've done, I must admit, it's still 100%. I'm not perfect, I must admit. I'm in learning mode. So let me just draw this out completely. Yeah. Right. Yeah. Right. So what we're saying is we've got 5 bar absolute across here. We've got 18 bar absolute across there. we've got 10 degrees C there. So that point there is actually at 10 degrees. Okay. That's a temperature which is going into the condenser, so the evaporator, sorry, from 10 degrees C. Also, you can work backwards and you get some notion of what the evaporator temperature is. That temperature there would be the bubble temperature, and here that would be the dew temperature there of the refrigerant, because the blend is boiling off. And to go further, so here we're coming out at 34 degrees C. 34 degrees. So that point there is 34 degrees C, and it's actually condensing something like, here's about 44, and here's about minus 40 there. But the more and more you get into it, it's actually getting the engineers to appreciate what they can see. I must admit, you need to be what I call a hyper-focused attention, because there's so many lines here. And what would be here would be the actual discharge line temperature. Now, some engineers will actually go on site, system running, they go to the thermometer, put it onto the discharge line, and they'll get the temperature. And here, that's 64 degrees C on this case. Now, that's with a thermometer. So here, the 34 degrees C would be the liquid line temperature on a system, measured with a thermometer, and then the 10 degrees C with the thermometer is doing that. Now, certainly looking at some of the new technology or requirements on learning, certain engineers don't actually use the discharge line temperature to actually plot. They can do. What's been tasked, what the engineers now being tasked with is, can they read the pressure diagram so normally I'd tell the engineers, look, we've got 64 degrees C, find that. What they're saying now is that still happens, so it still happens. We still use on the F-gas qualification, but more so on the endpoint assessment scenario, we're saying, look, so this line here, okay, this line here is diagonal, and it's diagonal in parallel to these lines. These lines there, or these lines. Now, these lines are what we call isentropic compression. Okay. They have the same entropy. Now, that's another word. Gosh, don't even go there. You've got enthalpy. We struggle to get that information across to certain engineers. And enthalpy. Entropy is something that's different. It relates to temperature and heat together. Okay. I could do an hour session on entropy, I won't. But certainly, what we're saying is, when the engineer doesn't know what the discharge line temperature is going to be, then they have to follow from 10 degrees C a line parallel, which is on the isentropic line there. And that comes out, that gives you a discharge line temperature at 64 degrees C. Moving on then, you've got label, you've got point A, point B, point C, point D. Now, point A is where it's going into the evaporator, point B is where it's going into the compressor, point C is where it's coming out of the compressor discharge, and point D is the liquid line going into the expansion device. So I'll just use this as reference, because I'm going to use these to get more information about the pressure resistor diagram. As the system is operating, we have to look at key points around the system. Okay? And A, B, C, and D. And what we do is, from point A, we would look at what's the heat content at that point. How much heat is there in the refrigerant at that point A. So what we're doing, we'd actually get the enthalpy. And how we get the enthalpy is we're looking at these values down here. Okay? And we draw a vertical line from point A to get what the value is there. From point B, vertically downwards to get the value there, and then from point C to get the value there. So we're doing vertical lines downwards to obtain what the enthalpy is. Okay? The heat content per unit mass, kilojoules per kilogram. So here, the difference between B and A, that's the cooling effect, refrigeration effect. And that, by calculation, would be the enthalpy at B minus the enthalpy at A. That's the refrigeration. Again, maths. Yeah. taking away two numbers. So we calculate the refrigeration effect using HB minus HA. Then here we've got heat of compression, compressor. And again, it's the difference between C and B. And so heat of compression is HC minus HB, and that's going to give us a certain amount of heat content. Then we've got the condensing effect. How much heat are we rejecting? Condensing heat effect. And that's going to be C. Now, technically, it's going to be the enthalpy at point C minus the enthalpy at point D. However, D and A are the same value. They're the same vertical. So that was the same enthalpy. So here, and that's going to be HD minus HC, but we can use HA as well. So, and that's the expansion process. So again, remember, evaporator, compressor, condenser, expansion device. Refrigeration effect, heat of compression, density effect, explosion. I'm going to now just pick up those formulae, because those formulae we can actually use to actually get the context the other systems operating. So what we're saying, we've got refrigeration effect, which is HB minus HA, heat of compression, HC minus HB, density effect, HC minus HD, and then going back to the diagram, we can actually pick up what point HA is. It's 250 kilojoules per kilogram, the value. So that there, vertically down from that point, 250. Here, going into the compressor, it's at 420 kilojoules per kilogram. And then coming out, it's out of the compressor, it's gone up to 450. So, on entry to the evaporator, it's 250 kilojoules. The heat has gone from 250, so the enthalpy has gone from 250 up to 420, and then from 420 it's gone to 450, then eventually from 450 has to get back down to 250 to process mechanics to make sure the system is operating again. And as an engineer, to see how efficient the system is, we do those calculations. So we've got HA 250, HB 420, HC at 450, and HD at 250. And I'm just going to be using these formulae to get the various bits and pieces. So refrigeration effect is going to be HB minus HA. That's 420 minus 250. That gives us 170 kilojoules per kilogram. So we're actually absorbing 170 kilojoules per kilogram of mainly latent heat in the evaporator. That's the refrigeration effect. To actually make that happen, the compressor has to work. So we've got heat of compression, which is HC minus HB, and that's 450 minus 420, and that gives us 30 kilojoules. So the refrigerator, the evaporator is absorbing 170 kilojoules per kilogram. Heat of compression, the compressor adding another 30, then that results in a condensing effect. So whatever heat we absorb in the evaporator, plus whatever heat we add in the compressor, has to be rejected. So the condensing effect is going to be the 450 that was here down to 250 there. So the condensing effect is 200 kilojoules. And notice we've got 170 heat being absorbed, 30 kilojoules of heat of compression, add the two together, and lo and behold, we get 200 kilojoules. Now, if the system is not working properly, then this heat, they should marry, the value should equate. So refrigeration effect plus compressor equals condenser. Now, for example, if they don't marry, they don't match, then that's as a consequence of the system not working properly. You might have a blocked condenser, you're not rejecting the heat, so the heat is retained and the system is getting hotter and hotter. So if everything gets hotter, it means your food is going to get hotter as well. Not like a microwave, but it's not going to be at the correct temperature. So refrigeration effect, heat of compression, condensing effect. Now,
yeah, I'm mute. He's mute. I can't hear anything again. You there, Paul? Lost audio again.
You also have ER and EH as well. What I'm going to concentrate on for now is just looking at coefficient of performance, COPR. Now, coefficient of performance is how much efficiency am I getting on the evaporator, at the evaporator. So we're saying to calculate the COPR, we calculate by refrigeration divided by heat compression. So that's 170 kilogram divided by 30. That gives us 5.7 to 1 as a COP for refrigeration. Now, if we look at the COPH for heating, for a heat pump, then it's a similar format, except we're using the condenser, so the condensing effect divided by heat of compression. So we've got 200 divided by 30, which is 6.7 to 1. Now, so we're getting COP refrigeration 5.7 to 1 and the COPH of 6.7 to 1. One thing you'll always notice, unless there's something wrong with the system, is that any refrigeration or air conditioning system is more efficient running in heating than it is in cooling. So here we're getting a COPR of 5.7 to 1, and here we're getting a COPH of 6.7 to 1. COPH is always 1 greater than COPR. I must admit, I'm trying to explain this to you in a format that you can relate to. I've got air conditioning at home. I'm forever trying to tell my wife, Jacinda, let's slap on the air conditioning. No. She said, we've got gas, these are nice. I said, look, and the way to explain it is this. So please can I have your ears. What I'm saying is, in this mode here, it's cooling, if we put in 1 kilowatt energy or heat capacity, the compressor is consuming 1 kilowatt today. Now, what you're going to be doing is you're actually going to be getting 5.7 times that. So think about you got 1 heater that's consuming the energy, but then that heater is actually it's using 1. Okay. Now on the air conditioning cooling side, what I'm saying is we got 1 kilowatt, and then we're getting 5.7 times that, so we get 5.7 kilowatts of cooling. And so it's over 500% efficient. On the heating side, think about this: we got 6.7 to 1. So we got 1 heater, which is consuming 1 kilowatt. So you're actually paying for 1 kilowatt of energy. Don't even go with the price of electricity now. But what we're saying, we're paying for 1 kilowatt. But what we're getting out heating-wise through the air conditioning system, heat pump system, is 6.7 kilowatts. You'd be foolish not to have air conditioning. Foolish not to have heat pumps. Because what we're doing there is we're paying for 1, but we're getting 6.7 times. No-brainer. With the pressure dial also, we can use an engine used to cooling capacity. You might have an air conditioning system at home, or you want one, and the engineer might say, well, you actually need a 2.5 kilowatt air conditioner. What that actually means is that the cooling capacity is going to be a value. And then to work out the cooling capacity, we have to take into consideration the refrigeration effect. And with that, flow rate of the capacity, kilowatts equals mass flow rate times refrigeration effect. And as an example, I've actually used 3.5 kilowatts. So we've got 3.5 kilowatt con unit, and we need to calculate the mass flow rate. How we calculate the mass flow rate is cooling capacity divided by the refrigeration effect, and that is going to give us. So we've got mass flow rate 3.5 divided by 170. So that's the cooling capacity divided by the refrigeration effect, and that's giving us 0.02 kilograms per second. And that 0.02 kilograms per second is circulating around the pressure density diagram. And on a pressure density diagram, direction of flow is always anti-clockwise, always that way. So we've got 0.02 kilograms there a second. We've got 0.2 here, the compressor. So what we're saying here is, if we know what the mass flow rate is, 0.02, and we know what the heat of compression is, we can actually calculate. We can calculate what the compressor input power is. Okay, so we've got mass flow rates of 0.02, we've got the heat of compression of 30, and doing the simple maths, 0.02 times 30, okay, that gives us approximately 0.6 kilowatts. So we've got a cooling capacity of 3.5 kilowatts. Compressors consuming only 0.6 kilowatts of the energy, and so that's giving us compressor input power and cooling capacity. Now, technically, whatever cooling capacity we've got and the compressor input power, if we add the two together, that should be what we reject at the condenser. So what I'm saying is, the condenser heat rejection is mass flow rate times condenser effect, and that's 0.02 mass flow rate. 200 kilojoules per round is what we're rejecting at the condenser. So technically, we're saying the condenser heat rejection rate is 4 kilowatts. So if you think about it, approximately we've got 3.5 kilowatts there, we've got 0.6, add the two together, 4.1. And the discrepancies that you're rounding off. So what we're saying, we have a cooling capacity of 3.5, this system is consuming 0.6, and we're getting 4 kilowatts of the condenser capacity. So that, what I've shown you there are some of the questions, some of the things that you can actually pick up from a pressure NVQ diagram. You can actually analyse how efficient the system is, not for that matter. I mean, for example, saying 0.02 kilograms there, if there's a blockage or a restriction, that 0.02 won't be flowing, and that will have an adverse effect on the component.
So what I'm going to just quickly ask is, looking at the presentation that you did today, if people were to take away nothing but 3 things from it, what would you say those 3 things should be, and why are they so important?
I would say that there's very many things that you should take away from the presentation. One thing that get to understand the basic refrigeration cycle. Understand how the basic refrigeration cycle is plotted onto a pressure NVQ diagram. Take a chart, let's look at the plotting side of it. And then most importantly, if you know how the refrigeration cycle is operating, and you know what the pressure NVQ diagram is, then do the calculation properly. So it's understanding the basic cycle, understand how to plot the system, and how to understand those are three things I would actually require and recommend. Is that okay?
Perfect. We do have a question that's come in from somebody who's asking, what would the benefits be of using zeotropic refrigerants that have a guide or sliding temperature?
The advantage is that we're getting a better temperature range. The system is running more efficiently in the sense that we can get down to low temperatures. The compressor has to work better. It's having efficiency on the compressor.
We also have a comment that I think complements the presentation. It's come in and it said, thank you for your presentation. What they're saying is there are a couple of compressor manufacturers' software that will allow you to select the compressor refrigerant and change some of the parameters, and it will also display the enthalpy chart, so you can see how subcooling, lifting, evaporating, and reducing the temperature improves performance. So thank you for sending that in, Lawrence. If you're interested in looking at more of the webinars that we've been putting out as masterclass, just go to the IOR website to ior.org.uk/even masterclass, and you can find them all there. Our next masterclass is happening on the 11th of April. Ian Fisher is coming back to do a case study on how to service the heat pump, and we are very much looking forward to welcoming you to that. So once again, thank you, Paul, and we hope to see you all on the 11th of the 4th.
Thank you, guys.
Right. Okay. So what we're saying is that I'm in a better light now. Actually, I've actually just realized, remove myself total light. I'm getting better. So there we are. But so, Gareth, how's that for you? You're on mute, I think, Gareth. I can't hear you. For some reason. Gareth, will you unmute yourself? Is it me? I can't hear you, Gareth. Is it me or? For some reason. Sean, can I hear you? Sean?
Yeah, hello.
Sean, I can hear you. Gareth, I can't hear you for some reason. Hey, Sean. Gareth, I'm trying to get your audio back on. Whilst waiting, Sean, I mean, there's a fair bit there, wasn't there?
Yeah, I'm definitely going to go back and listen to it myself and go through the bits, but understanding the chart and using the vertical lines to understand.
Yes.
So knowing, like when it went to 407C, I was thinking, I could see the 20 bar mark, and I'm thinking, I think I want to be just below that. And then when it came at 18, I went, right, I kind of getting this a bit now.
Really?
I'm sort of thinking where it's going to go there now. But
Ah.
then where the curve comes like this, and then that little bit where it says that's your discharge from your compressor, from that first dot to that second dot, and knowing that's my discharge line. And if I'm correct, is that now that's the subcooling from there? Is that right? From that, or is that the superheat? Yeah, man.
Yeah. So I've got
so
somebody in the background. Sorry, Sean. I've got
the
window cleaner comes clean. My window is raining.
I'm just having a better understanding now of that relationship of how that starts.
You know, it's not the end. This is the beginning.
Yeah, and how the arc, and I'll just obviously I'm not going to pick it up in one.
No.
In one.
I don't expect that. What this is about is actually, setting the foundations for you to build on.
Yeah,
that's vital. Okay, Gareth, can we hear you now or not, Gareth?
Can you hear me?
Yeah, we can hear you. Great stuff. How was it for you, Gareth?
Yeah, a lot of information, like Sean said, but the sound was going in and out, so I definitely want to rewatch it again.
Yeah, I think it'll be better on screen. I'm hopeful that the recording will be a lot better.
You're picking up. Do you know what I think it was? I think whenever we move it
I think I'll move the mouse. So I was trying to get myself sorted out. But yeah, certainly have a look at the IOR website, ior.uk. And then it's free entry to look at that. And then you can, I'll get you signed up for other webinars as well. So I know there's a lot to take in. And this is just the beginning. And I'm hopeful that we're moving in the right direction. I mean, you have PowerPoint slides to look through. Forward. James, how was it for you, Al?
Yeah, quick in and out. Was getting the gist of it with the empathy charts and the basic diagrams and how the subcooler and how the superheat was working. But I will go back and register and actually watch it again, where it's a bit more clearer.
Okay, it's probably a different way of learning in the sense that I've focused on asking you not to write anything, and that's difficult. Yeah, and that allows you to actually concentrate on what's being said and what you can see. And the beauty of it is, I'll record this, put it onto YouTube unlisted, and send you a link so you can actually view it at leisure. And this is, I would say, it's a very unique experience, learning experience, and again, relax, participate, enjoy. That's what I want to do. I'm not going to set you any homework now. Okay, there is a follow-on. There's like question and stuff like that. Other handouts I want to have a look at. So I'm conscious of time, and it's 20 to 9. Do you have any questions on what we've done in this session at all?
No, not right now.
No.
I think I might do once I've watched it and sort of take it in a bit more.
All right.
Probably might write it down once I've watched it this week, ready for next week.
Okay. So do you think, I mean, I just want some feedback of how the session's gone for you. Is it what you expected? Is it better or worse? Different? Any comments that you make would be good, because people can actually hear on the recording, what your feelings are. Really would appreciate a few, comments, your personal feedback.
It's definitely different. I think most courses we've ever done, especially online, a lot of them you sort of take notes, and there'll be sort of questions and answers that you've got to pass at the end, and
yes,
so you tend to write a lot down, don't you, just to cover yourself, that sort of thing. So yeah, it's different in that sense. But
okay, so I mean, what really will come together is there will be opportunities for you to write the stuff I want you to write down, the salient points, the bits and pieces, or there'll be homework to look at something, fill bits and gaps, stuff like that. But at the moment, I'm just trying to get you to the situation where you have a better grasp of what you're handling out on site, and build up your confidence very, very quickly, because knowledge is confidence. So this is not the beginning; it's the end. It's not the end. Sorry, it's the beginning, and I want to put that forward as a group. Sean, any feedback on the session?
Just where we've said we're going to go back and watch that video on the IOR.org.uk masterclass.
Yes.
Can we just have, so the beginning of next week, can we have like the first 10 minutes where anyone's got any questions, we can just go through them quickly? Because I know,
of course.
I know for fact, I don't want to take more time of teaching, but I know there's going to be a few questions I need to get my head around.
Sean, Gareth, and James, if you do watch it, don't wait till next week. Drop me an email, drop me a text. I can answer them then. Don't wait till next week. You're going to be pondering over it for 7 days or so. After you've viewed the webinar, if there's any questions, just fire them at me and I'll answer them, by email or by text or by phone, So, don't wait till,
your number's on the bottom of that email, isn't it?
All right. James, your first session with us today, and how's it been?
Yeah, it's like I say, it's been different. I'm used to writing notes and
I know.
keeping up.
It's something I have to. It's something I have to try and stop engineers not doing. It'll come. I mean, I know you're not available on Saturday, because James lives close by to our training centre. I did offer him an invite to come in on Saturday morning that we do at the centre in Birmingham, and they can't do that, but sometimes there will be. And I'll be inviting both Sean and Gareth down to my centre when we do the practical assignments anyway. So if there's no questions, I've really enjoyed it. I've taken some photographs. It's being recorded. There are lots of people out there who want a link to this. People who aren't on the call. Is it okay if I actually pass the link to this video in particular to my other contacts? Is that okay with you?
Yeah, fine. Yeah.
There's no there's no GDPR stuff like that. We haven't spoken anything about confidential about your work, stuff like that. So, with your kind permission, that's what I want to do, and hopefully that will bring up more business, And I will be doing a LinkedIn post, so don't be surprised if I quote you or mention you on LinkedIn about how this session's gone, and then that'll be better. So not only are you getting the learning, you're getting the actual publicity that goes with it as well. All right. Okay. If there aren't any questions, chaps, really, really enjoyed it, and I'll see you next week. All right.
Thanks. Enjoy the rest of your evening.
Thank you. Bye-bye. Bye-bye.